All right. So now that we've done thermal expansion and contraction, by the way, I don't think I've made a big enough point of this, but let me say that clearly. These changes of dimension that I'm talking about here can be decreases of dimension just as well as increases. And we tend to get lazy and sloppy and talk about thermal expansion, but it's really thermal expansion and or contraction. So things generally get smaller if their temperatures decrease, right? But anyway, that said, our next move is to go into two dimensions. And so where both the length and the width are comparable, and so we need to care about both of them, but we'll assume for this analysis that the thickness, the third dimension, is still small compared to the other two. In which case we talk about the coefficient of area expansion. Actually, what we talk about is the coefficient of thermal expansion or contraction. That's still alpha, so we're still going to be using the same alpha. Reason is we're still looking at something that's a property of the particular material that's heating up or cooling down. But anyway, the area expansion or contraction will reasonably enough be the product of the, or at least related to, the changes of dimension in both the length and in the width. And it goes like this. It's pretty straightforward. So without much regard to the specific geometry involved, obviously an area could be square, it could be rectangular, it could be circular, it could be an arbitrary shape. But anyway, it's two-dimensional. There's no reason to overcomplicate things, so we'll just go with length times width as the way that we're going to calculate the area of our otherwise arbitrary object. And as you'll see, the details of how to calculate the area are going to end up being fairly irrelevant anyway. But let's see how this works. So area, the area of some object, call that capital A, is calculated by multiplying its length times its width. The thing is, though, if we what I should be writing here, let me make it clear what I'm calculating. What I'm about to calculate here for you is the change of area, or the final area of the object after its temperature has changed. So I probably should be writing A sub F is equal to L sub F times W sub F, for final values and then the initial values. The equation is going to be cluttered enough as it is, so I will use subscript 0 to indicate initial values of the variables, but I'll leave out the subscript F just to keep the equations from looking too horrible. So without the subscript, then these are intended to be final values, unless of course I put a delta in front of it. Anyway, so the final area after the temperature has been changed of our object is going to be the product of its new length times its new width. Okay, and again, keep in mind that delta L and delta W can be negative, will be negative if the either the length or the width, or perhaps both, contract. Usually both would go the same way. Okay, and so this becomes, and so this is just the product of two binomials, so we have, I'm sorry, L, W naught there. So we have L naught times W naught first outside, plus L naught delta W inside, plus delta L W naught, and then out last, delta L times delta W. Okay, but of course, the order in which you do the multiplication doesn't matter, first of all. And second of all, delta W here is going to be calculated. In fact, let me, you know how I like to do color coding. So let me do some color coding here. And let's see. I'll make delta W purple, I guess. And I'll make delta L blue. Okay. But delta L is calculated by multiplying alpha times the original width times the change in temperature. Okay. Plus delta L, and delta L is alpha times L naught times delta T, plus delta L, I'm sorry, I missed a W there. I did too much erasing there. Hang on. Okay, so purple, blue. So blue. Delta L times W naught. So delta L alpha L naught delta T times W naught, and finally delta L alpha L naught delta T times delta W alpha W naught delta T. All right. So now what I'm going to do is multiply things through, combine like terms, rearrange stuff, and when I do, I get L naught W naught plus alpha times delta T, so I'm factoring out a common factor, of L naught times W naught, so there's L naught times W naught there, okay, and plus W naught times L naught, okay, with a common factor of alpha delta T taken out, and then over here I have plus alpha times alpha alpha squared, L naught W naught delta T squared. So we have alpha squared, L naught W naught delta T squared. Okay. And so then what do we have? Well, L naught times W naught times L naught, obviously those two things are equal. So that picks up, that's just one of these with a factor of 2. So L naught W naught plus 2 alpha L naught W naught delta T plus alpha squared L naught W naught delta T. And now what I want to do is look at this and say, okay, I have L naught W naught here, L naught W naught here, L naught W naught here, and that's as far as it goes. It should be squared here. But the other thing I want to take note of, you remember from the previous example that alpha is for almost all materials, is a very small number, on the order of 10 to the negative 6 inverse kelvins, right? And so alpha squared is going to be 10 to the minus 12, plus or minus a little. All right. So alpha by itself is already a small number, indicating that the changes of dimension are very small for per Kelvin degree temperature change, per Kelvin temperature change. So alpha squared is incredibly small. It is so small, in fact, that this third term here is really small compared to the other two. And since everything we're dealing with is very small anyway, and our ability to measure such small changes is not all that great anyway, I am entirely justified in just neglecting this last term as a tiny, tiny numeric correction that I could probably never measure in practice. And so as a practical matter, I can just ignore that, and we have L naught times W naught times, and now I'm going to factor things out. Well, no, I don't care. Well, I'll just go plus 2 alpha L naught W naught delta T. So that's approximately equal to there. Okay. And all I did was neglect that last term here. Because it's small. Okay. However, here we go. What have I calculated? Just remember, I'm calculating the new area of our object after its temperature has changed. But this thing here is the original area, right? Its original length times its original width is its original area. And so this thing here, evidently, is the change in the area, okay? And that's what we're after. So surprise, surprise, the new area is the old area plus how much the area changed as a consequence, and so we end up with so connecting the very beginning and the very end. The final area after the temperature change is the initial energy, initial area, sorry, plus 2 times alpha alpha A naught delta T. Okay? And the change in area is A minus A naught, final minus initial. And so the change in area is simply 2 alpha A naught delta T. And compare this relationship here, this result, with the one for just linear expansion in one dimension. And the comparison is this has a factor of 2. Okay? And yeah. And the factor of 2 is a direct consequence of the fact that we're now looking at an object in 2 dimensions. And so that's it. All right, so that's the theory. Next recording, I'll do an example of this, and then we'll go into 3 dimensions. And if you think about it for a moment, I'll bet you can predict what the result is going to be, what the expression is going to be for 3 dimensions.